Hello and welcome to our fourth Arch and Z webinar. This event was also held in person, so there'll be a mix of clips today between the live event and the webinar. If this is the first time that you've had that this was also in person, please make sure to check your emails from us at Global Survey all about the in-person events where you will be able to sign up for future in-person events. So on the agenda for today, we're going to look at automating reality capture with ground robotics. We've got Haydn Bradfield from DroneDeploy, the same one who used to work for us at Global Survey, who's going to be doing a talk for us all about this. Please save any questions that you have for the end of the talk. Just make sure you put them in the questions tab as we go. And then we'll have a little look at what's up next with Arch NZ. So first, who am I? My name is Kirsty Mackey and I have experience in reality capture workflows from two main companies. I started at Asbuilt, a small but impactful company focused on scan to BIM and visualization workflows. There I worked on some very large scanning jobs that took several months, requiring hundreds of RTC 360 setups a day. I can tell you that a robot would have been very handy back then. Then I worked at Beckett in Wellington in the survey team, focusing at first on high precision topographic survey, and then later expanding to the applications of reality capture to the wider business. I've been at Global Survey since January, so still pretty new. I am the new reality capture and autonomous survey BDM for the North Island. I'm particularly passionate about the onwards destinations of all of this point cloud data and how it's being used. And that's great because it's one of the main aims of this Arch and Z group that we have. So I'm just going to go over some of the aims of this group because we have quite a lot of new faces today joining our group. So our aim with Arch and Z is to create a reality capture user group for New Zealand. We want to build a community for networking of all these reality capture professionals. And then we want to go on to providing a platform for discussions around reality capture. Point clouds are often not the end of all of our reality capture workflows, they're just often the beginning. So understanding all the potential uses and onwards environments of this data is really important. And thirdly, we want to focus on the future of automation in capture, processing, and delivery. Anyone can sign up through our website to this group. So if you have any colleagues that want to join in, just send them the link online, just search Join Arch and Z Global Survey in Google and it will come up as one of the first links. You can watch all of our past webinars online there. So today really highlights our focus on automation. Autonomy is about how robots, sensors and software work together to eliminate as much physical work as possible. How can advancements in robots, Grand Slam, real-time data processing, AI, machine learning, and much more improve efficiencies in the management of reality capture data? And this is going to be one of the big questions in Arch and Z going forward. Automation is already changing the way we're working. For scanning, we have setup-based workflows, but there's now also handheld devices, and coming soon is autonomous drones. Hopefully we'll have the BLK to fly in the country to give you some demos of. And then we have robots like the Boston Dynamics dog that we will be looking at today. This is really shifting the role of many professionals in our industry, and we're all having to adapt a lot. So it's great to be part of this community so that we can continue conversations and not be left behind. So today's speaker is Haydn Bradfield. He's trained as a civil engineer and has worked as a site engineer for some large construction companies in New Zealand. As I said before, he used to work at Global Survey, so he's very knowledgeable on all things reality capture. And now he is a product specialist for DroneDeploy. So hopefully you will help us not be left behind, Haydn. I will now pass over to him.
So a little bit of what we're going to cover, a little bit on reality capture, small piece on DroneDeploy, just about the acquisition really, and then we're going to go into ground robotics. And I was hoping to be more of a interactive than a formal presentation with you guys and actually showing how ground robotics actually work and talking through some use cases and some other customers around the world that are doing some cool stuff. So as Kirsty sort of mentioned, I started off as a civil engineer. I thought it was awesome. And then I got picked up by a construction company, got to work on some really cool projects around the world where I got to be real frustrated with how construction works and got really into like construction data and land and surveying. Obviously engineering surveying, not the smart land surveying that other guys do. And then Mike actually picked me up, which was great. He got me from Vanuatu to New Zealand, which I'm very grateful for. And basically ended up on the Pua to Walk With project doing a lot of drone surveying and engineering survey. And then Fletcher sort of got me into this role of digital engineering, which lasted a fair bit. And then decided to take a break and join Global Survey, where I got to learn a heap about reality capture, which was awesome. I then got a real good opportunity to work for DroneDeploy with basically this hybrid of knowledge and of the industries. And I get to travel the world now and implement robots on some of the biggest oil and gas and engineering type projects in the world, which is awesome. So yeah, that's a little bit about me. Why are we getting into reality capture in the first place? I guess I probably don't have to explain to you. Reality capture is a perfect tool of capturing that visual record at that point in time. You can't lie to the photos unless you can Photoshop every single photo or whatever you've captured. There's no lying about it. It is the truth. Usually these things are all geo-referenced. It's in place. So you get this amazing record of time of what's happened where, which obviously becomes very valuable in a construction sense for whatever claims and things have to happen. And then obviously it's a survey tool as well if you can get your accuracies real good. DroneDeploy basically tried to dominate the aerial space, which they've been fairly successful at. And then there was this massive need for customers to do facades and inside buildings, because when a roof's on a construction site, then the drone's almost like useless again. So they came up with this idea that they needed to do some really good ground capture stuff. So they acquired this little company in New Zealand, which was called Robotics at the time. And Robotics was a robotics software company that was integrating with a bunch of robots to do a bunch of cool things. One of them was early days, obviously being Spot. A little bit about why we do ground robotics. Obvious sort of 4 things which you might have heard before on other webinars really. We want regular repeatable inspections, especially if it's progress monitoring. If we want that visual record and reality capture over and over so we can jump back at any point in time, we want repeatable inspection. So there's an element of repeatability that the robot can do, which a human's probably not going to do very well. Hazardous environments, we basically want robots to do dirty work. That was a little robot that I made. I call it Robot. It's a remote control car that carried a little BLK 360. And that went through a building that was sort of ravaged by a fire a few years ago. You could probably guess which one it was. And that did a great job. Basically, the solution that the construction guys got for us was like super expensive, took weeks to do. And I basically smashed an iPad and damaged the laser scan in like the first day of trying to use their solution. Took us a week to build that, and we covered the whole area in like 3 days now was it. So real good use case in that sense. Remote sites, more sort of relevant to the oil and gas industry. We have massive, oil and gas facilities in the middle of Texas that have no people around for hours and hours. We have customers that deploy robots there through sort of software and smarts and really good internet connections. We can basically control the robot, get eyes through the robot, and do a bunch of stuff as if we were there in person. So it becomes a really good tool for being on a remote site and being able to do inspections, capture data, have that data pushed to a cloud where they can get it in the office. And then your basic stuff like automating very low value tasks. Customers that we have that have robots that spread fertilizer around a farm autonomously, plant seeds, go and count crops with AI, a whole bunch of stuff like that. So real low value tasks that the person would go around and do inspections, we can get robots to do. Another one which is coming up at the moment we're working on is, it's a solar farm that you can see from Google Earth. It's massive, and it takes guys like 6 months to actually cover that whole area to do visual inspection. So we're deploying robots there to autonomously every day just walk up and down, take geo-referenced images and load it to their cloud server. So those are basically the use cases of robots and why we want to do robots. And now, obviously, a drone's got a really nice gimbal camera, or you can have a thermal image payload or a LiDAR unit on a drone. But with the ground robot, because it's so powerful and it's so capable and it can take a lot of heavy weights, we can start chucking a whole bunch of other sensors. Obviously, we want to make the robot valuable. So we want multiple sensors on the robot to do multiple things. And just as an example, Spot comes with a Velodyne sensor on the back, so it's already got a LiDAR sensor. This one in particular doesn't have it because we're still waiting for the new one that's coming from Boston Dynamics. We've got 360 cameras on there that do this thing called 360 walkthroughs in DroneDeploy, which is a very, very popular tool for documenting sort of progress, which I think I'll give you a show on a bit later. And then the oil and gas guys are obviously into the thermal imagery, they're into the gas sensors and things like that. So what we're doing with the sensors is typically like a person, and I use the oil and gas industry again, would be able to carry 1 or 2 sensors, and it maybe, maybe another one in the backpack, and they have to manually walk, take whatever imagery. If it's not connected to the internet, they'll get back to the office. If it needs a battery, they have to have battery packs. Basically, everything's powered through the robot, everything's connected to the robot. And when a picture or a piece of data is collected, it gets pushed up to whatever cloud where it needs to go autonomously. So data handling, the actual effort of carrying all this gear, the robot carries that. And that's the purpose of sensors. But as we learned today, robots are really complicated. Robots are far more complicated than what people expect. And we've come a long way with drones. And I can confirm this because I used to watch Mark in 2018 with a very big drone getting very frustrated. So there's a little quote which I'll quickly mention first, is that like the ground robots are probably like a decade behind where drones were. So where we were struggling with like really big drones with really clunky sort of user interfaces and a whole computer unit to put on a tripod next to the drone and PPK timing issues and all that, we kind of in that stage where those frustrations are real. Today's an example. And in 10 years' time, we're going to be taking for granted those issues with robots like we do for drones now. We just turn on a drone, we get onto whatever software, we plan a map and it goes and it takes photos. So in 10 years' time, like it's probably going to be, we can walk into PB Tech and there's a drone on the shelf, a robot on a shelf with a bunch of payloads. They clip in, they just do the job. At the moment, there's a lot of like configuration and hair pulling and things that can go wrong in the stage. So anyways, let's compare it to drones. Typically, as a drone in these days, taking nothing away from drones, obviously, because drones have come a long way. We've got drones with 4 propellers. We've got a gimbal camera on it. It's lightweight. It's got, usually it's in the sky, so it can get like a GNSS signal. So it's positioning, its stabilizations, or like helped with the GPS. I say GPS, so forgive me. I'm just going to say GPS because it's easier for the purists out there. And basically, when the robot's struggling with the wind, the IMU is compensating, and variable motor power is going to variable power is going to the motors to keep it balanced, right? So fairly straightforward concept. Obviously, there's a lot happening, but it's very straightforward. Again, it's got GPS the entire time because it's in the sky, and there's no obstacles in the sky besides for maybe a bird or an airplane, but you shouldn't be in that space. So when you say to a drone, I want you to plan a mission, and it means take off to a certain altitude, go to certain places, trigger a camera, and off you go, it's really straightforward. It's really, really straightforward. And a drone, in fact, is not actually fully autonomous because you still have an operator turning the robot, the drone on, getting the controller, planning a mission, saying start, checking everything's okay, arming the motors, and it takes off and it lands. And then you pack it up again. So it's not fully autonomous. The flight's autonomous and data collection's autonomous, but a drone itself isn't actually yet fully autonomous. Except for when these other cool things like DJI drone in the box and things. I don't know if you guys have seen that or heard about it, but we obviously very close partners with DJI from the DroneDeploy perspective, but there's going to be some drones coming out real soon that sit in a little box and open up on their own and take off and land and charge and close again. So it's completely autonomous. You'd be putting those on a construction site to be doing drone surveys every day, basically. So let's compare it to a robot. If you think about, again, with respect to drones, how simple a robot or a drone might be. We've got a robot, and robots come in many form factors, and each form factor solves a different problem. Spot's a quadruped, which means it's got 4 legs. It solves a unique set of problems like going upstairs. In terms of like longevity of battery life, absolutely useless robot. If you want to put it on a wind farm or a solar farm to do anything long game, would not choose that robot. You'd choose something that's on wheels or tracks. So each robot's got its own form factors. We're going to focus on quadruped today because obviously Spot's in front of us. There's a lot of complicated motors in there, and a lot of motors doing different things and not straightforward doing, a linear movement. It's doing like 3D movements if you look at how the shoulder joints and all those type of motors work. So the motors become real complicated, and it is also very heavy. Another varying part is that we have multiple sensors on it. Each vendor creates sensors in a different language, programming language. The robot's in its own programming language. The computer on the back's got its own programming language. Everything's different. So there's all those complications. when we come to trying to get sensors and things to work with each other because they need to communicate. We need some sort of translator. Stabilizing that robot. There's no GPS to like position itself, first of all. And the second thing is it's got IMUs and a bunch of sensors. If it needs to rebalance itself, it actually needs to take a step. And like typically we would kick it and show you what that looks like. We won't do that because I've already had trouble today. But when that thing needs to stabilize itself, it needs to move its position. Like if you're thinking about like a human, if I fall over, I balance myself, it does exactly the same thing. It needs to figure out when it puts its foot there, where's its center of mass with all these payloads going to be so that it can actually position its foot in the right place. So it ends up being very, very complicated in terms of its stabilization. So actually getting up and moving a robot of this nature is very, very complicated, and it's an achievement what Boston Dynamics has done. Like 100% hats off to them, they've done a great job. But we come back to this thing as a ground robot's usually on the ground, and a ground robot on the ground usually doesn't have GPS and it's indoors, and we're stuck with this problem of how do we know where the robot actually is. So you'll see these like little QR codes that are around. I mentioned earlier that Boston Dynamics has got a LiDAR unit on. That LiDAR is used for positioning. Obviously, it's what a LiDAR kind of does. So it's used for positioning itself. This one doesn't have it, so its navigation capabilities are slightly compromised, but I've put up these fiducials. Fiducials are April tags. Basically, the robot can recognize where they are. So when we tell the robot to sort of understand its environment, it looks at these fiducials and figures out where it is in the world, its world, not the world, its world. And its world starts off at 0, 0, where it starts, basically. So if I turn that robot on and turn it off again, it would reset and think that it's at 0, 0, whatever coordinate frame it thinks it's got. So it's real hard if you can think about the challenges of converting that into anything that's valuable for any type of survey or GIS type platforms. So we've got some smarts, which I'll explain, that our engineers have achieved, which is great, where we can actually start giving, like you would normal survey control, giving these fiducials either UTM or NZTM type coordinates, and then we get the robot to actually operate in a survey frame and then convert those into WGS84 so that we can actually use GIS. So all the data we collect can get WGS84 tag, go into a GIS system autonomously and be in the right place. And that applies, I'm probably jumping the gun here, that probably applies to something like the ARC as well, where it's in the survey coordinate frame, the ARC's information is also getting updated to that frame so that when it comes into your survey software as a point cloud, it's geo-referenced and ready to go. A lot of things complicated to do that, and but we'll get into that. And what we're also trying to do, which you've seen drone, this robot on Instagram and LinkedIn and doing all sorts of cool stuff. That's remote control. It's a $200,000 remote control car. We're trying to achieve full autonomy straight away. We're not trying to say we need someone to turn it on and make sure it's in the right place. We basically want to leave it on that dock and it's doing its missions on its own, on a schedule, pushing the data wherever it needs to go, and then charging and getting ready for the next one. And we've been able to do that. It's awesome. We've got some cool use cases which we'll go through. That's happening now, and that's a step ahead of where drones are at the moment, which is actually quite exciting, considering that they're 10 years behind, but the autonomy level is way ahead. And when I speak autonomy, think of autonomy as being, it's actually doing everything autonomous, even thinking for itself in a way. An automatic mission means it can go waypoint to waypoint to waypoint and waypoint. Autonomy means it can go to a waypoint, do something, think about something, and then branch off into maybe other, basically a thought pattern. If a something is something, go this way or go that way, which we'll show again. So we spoke about sensors. The reason we have robots doing cool things is we need sensors on the robots to do cool jobs. So we have robots that do, obviously we've got payloads. We call them payloads. So when I say sensors, I mean payloads. We got payloads that do some cool camera things. We've got thermal payloads. We've obviously got LiDAR units like the ARC and the native Boston Dynamics LiDAR that comes with it. There's obviously gas imaging and acoustics and sort of sound type things. You'll see in one of the videos I'll show you, there's a microphone next to the robot, which is really cool because guys in the diamond mining industry in South Africa go actually and listen to pumps. They go up to the robot and record a 30-second clip of a pump, and then their machine learning can actually go through that sound and figure out if the pump's working as it should or not, which is quite cool. But we come to this sort of thing where sensor developers or payload developers are a little bit limited in the way they develop robotic capabilities. Kind of went through how complicated robots are, but a lot of hardware manufacturers saw Boston Dynamics and said, wow, that's a cool robot, we want to integrate with it. So they ended up saying, all right, here's our sensor, and we want the sensor to be carried by this robot. And they went and developed the integration, and they kind of like tapped into Boston Dynamics' robot and said, well, sweet, this, let's get the robot to stand and move and do cool things. And that's kind of like their limit, really. And once you're locked in that workflow, you can't really put any other payloads on, and you're limited with that payload in particular. So the integrations that some of the vendors have made are either like spot specific or other type of robot specific, usually spot because it's just the one that everyone loves. And we call it a component, which I'll show you. The robot component is very limited in terms of function. So does the robot actually do robot things really well? Probably not. A little bit about our philosophy is that we're not saying we want the sensor on the robot, we want the robot to be carrying a whole bunch of sensors. So it's just another way of looking at the integration. Yeah, so basically the last question, not the second last one, is within our agent, which I'll explain now, on our platform and things like that, sometimes we have like a minimum of 6 to 7 different languages operating at one go. So the platform's got like a bunch of languages, the agent's running a bunch of languages, every integration is running its own language, and we basically had to overcome this challenge of developing a really cool holistic solution while dealing in so many different computer languages and getting the right information to pass to the right other pieces of software. And yeah, this industry in particular, or all the industries that are adopting robots, are going to have to rely on smart partnerships. And harmonious integrations, really. We can't just have a point solution anymore. Those days are gone. So a statement I've said to a lot of these providers, like a bunch of others included, is you've got to allow the robot people to do robot things really well, and then we will enable your sensors to do your sensor things really well. We can't jump that gun, which is why ROCOS wasn't sort of invented on its own however many years ago, just for that need in particular. It's just become more relevant in this day and age. So a piece of topic which is probably very interesting to you guys, because that's why you're here, really, right? Reality capture. So we mentioned earlier that Spot comes with the native LiDAR sensor. That is a very capable LiDAR piece of hardware. All right, so everyone who buys a Spot, who doesn't know robotics or who doesn't know reality capture, which is typically like a lot of people, they will read their invoice from Boston Dynamics and be like, there's a LiDAR unit, I'm paying for LiDAR. Why can't I have that middle picture? Why can't I have this beautiful scan from like an RTC 360? Because they've seen point clouds. They've seen point clouds on LinkedIn. They've seen everything. They see a line item on the invoice from Boston Dynamics that says, I got a LiDAR unit. Why can't I do it? And before I moved to a robotics company, I would have said exactly the same thing. And then I met my engineers that I'm working with. And different level of engineering, but we had real arguments until we realized that we weren't talking about the same sort of LiDAR function. We like mapping, and these Leica scanners are amazing pieces of hardware, and they do it really well. The Arc and the Go also like phenomenal the way they work. But the entire robotic industry doesn't care about pretty pictures. They absolutely don't care about anything on the far right there. They only worry about this thing on the left, and that looks ugly, as you can see. So basically what happens when that robot stands up and we tell it, hey, figure out your environment, it uses that LiDAR and it takes like snapshots. And you'll see later on, I'll show you a demo, there's like little green dots everywhere when it tries to figure out where it needs to go. And along these green dots, it's just taking a snapshot of the point cloud, really light point cloud, like maybe 2 hertz worth of points. It's just saving that. And when we repeat this mission, or we tell it to do something in this coordinate frame it builds, it's basically going to each one of those waypoints and using the live LiDAR, which is the live feedback from this VLP16 or Velodyne puck. It's basically trying to register itself. Register is a term we all get. It's basically registering itself to what it thinks it should be. And that's how it navigates through and actually remembers where it is. Now, that's a very complicated process. It's very hard. It's involving, obviously, like real-time SLAM. It's doing this thing. It's using vision sensors to navigate. So it actually doesn't care much about all the points. It doesn't have to be that accurate either. So there's no much effort going into actually like calibrating and fine tweaking how this works, like a arc or would have gone through an actual mapping piece of equipment. So it discards all those points. It never uses them again. So you've got this like really capable piece of hardware, and it's only used for navigation, and it only comes in like the intensity colors. They don't even care about the intensity colors, more of the positioning of the point. So for us to think like, hey, you've got this really capable sensor, why aren't we using it? We got this real long answer from the robotics. And the problem is, like, Boston Dynamics steals 100% of those points, which means if we had to try and tap into that VLP16 that's not on there now, when we try and tap into it, we cause a lot of chaos for the robot. But that picture on the left there, we actually created some just like really easy light software to go and try and record what the robot was thinking. And that's the product we got. So you can see in terms of like robotic navigation, their value on LiDAR is very different to what we perceive. And obviously the next one's like a RTC 360. That's the goal. That's what we want our point clouds to look. Real low noise, beautiful colors. That's what we want point clouds to look. That's what our environments we need. The next step is data set of the same area in our office of the BLK ARC. And that was very quick. That was walking through the environment really quick. It wasn't standing still for anything. I hadn't changed the way the robot walks. You can typically make it go slower, but I just boosted through there to make sure everything was working. And that's the product we get. So what Lark has kind of done here, which is great, this mobile mapping unit, is they've really started bridging that gap between a robotic SLAM system and like a terrestrial scanning or static scanning, beautiful point cloud. And where the industry is going to go, and we're talking like, this took me maybe 30 setups to do our office with the RTC, it was about 30 setups, which isn't very long with the RTC, but that ARC, that was 3 minutes walking through the office. So before basically one scan could be done with the RTC on like a high density, we've mapped the whole office with that resolution of type point cloud. So basically the efficiency gains of mobile mapping is one day going to like supersede the quality expectation of mobile mapping. And obviously as mobile mapping gets more and more accurate, that will start to become more, I guess what I'm saying is, at the moment, construction companies look at mobile mapping, they're like, we can't use this. I don't understand. Maybe it looks a bit messy, it's a bit noisy. I put it into my software and I can't go and do whatever clash detection I want. As that gets better and the efficiency, like the time efficiency is way higher, that value starts being seen. The use case I'm going to show you is like as a customer in the States. They're doing one of the biggest data centers for that little blue logo, which I'm not supposed to say. And they've got a robot that's scheduling like every 3 o'clock in the morning. It's getting up and walking an area and either doing a 360 walkthrough or doing laser scanning. And that then gets pushed through their pipeline ready for them the next day, and they sort of carry on. That then gets farmed out to another part in the world where they do a whole bunch of like cool clash detection. So really cool point cloud to BIM workflow. But they're adopting that because the ARC is good enough quality for them to be really efficient, provided they can get the data in like 5% of the time. So really cool use case for mobile mapping coming up. And one day we'll be laughing about how Haydn said mobile mapping wasn't good enough, and it will be the thing we actually do all the time, provided a robot can take it. So in saying that, obviously the ARC is brilliant, and the ARC is like really small and efficient. It colorizes the point cloud. It's amazing. This is actually, this could be mistaken for a terrestrial static. It's a mobile scan from a robot, from Spot, using very similar hardware to what comes out on the robot by default, which is very exciting to see. Also, it's not commercially available and it's very expensive if you wanted to do it, but that's where it's going. It's super low noise. It's really high quality. It's got SLAM algorithms that are doing loop closures. It's got a bunch of cool things that's happening in there, which is just showing that one day we're going to have mobile mapping that will supersede terrestrial scanning because of the efficiency that it is to capture that. That was probably like 10 minutes worth of walking around a facility. It's mapped the entire facility inside and outside. You'd never be able to do that with a terrestrial scan. So the future of mobile mapping on a robot, and obviously like Leica is leading the way, it's very bright. And the fact that a robot can now operate autonomously is even cooler. So a lot of fluff about point clouds and stuff. Our ground robotics solution, this is probably quite important to understand how we work. So we create this little thing called an agent. It's the smallest block there almost, but it's the most important block. That agent's architecture is designed in a way where we can basically deploy it on any robot type, provided it's running a supported robotic format. So the robot industry's got like a standard format called ROS. If you've programmed a robot in ROS, 99% that we can just deploy straight onto any ROS robot. Boston Dynamics chose not to use ROS and be difficult, so there's a whole other piece of the agent that we had to develop for the spot component to work, but it works really well. So basically from your left to your right on robots, that's a robot from Spain, which works on our platform that's going to Peru on that solar farm. The one in the middle is a Canadian manufacturer. They run our software by default. It's just one of the things they sell as part of their robot solution because of the capabilities you'll see quite soon. And obviously we've got Spot. So the agent, think of it as like a jockey riding a horse. The agent is installed on that little silver computer that's on top, and that basically, it's the jockey. It controls the robot, and it's got like these tentacles that go into Spot. So whatever robot it is, it's got these tentacles that go in and say, I'm going to control you now, and you're going to give me information. So we receive telemetry, we give actions. And then on the side of that, we've got these things called Docker containers. For the guys who understand computer programming, basically Docker containers are little operating systems that run on the side so that you can easily deploy them and turn them off, and you don't actually like creating a whole new version of the agent every time you want to change a component of the agent. So within our Docker containers, we've got a bunch of integrations, some of them Fleur, the Insta360, obviously the Leica Arc. That little component there has been causing the chaos today, but basically we can turn those on and off, and if you have a different sensor, we just turn it on and it works in the agent understands it, and off you go. So once the agent receives all this information from the robot, and it's obviously tentacled into the robot, plus it's got its backpack of all its containers and software that we've developed, it then goes up into this cloud platform. So obviously an internet connection is very valuable here. It needs to have an internet connection. Once it has its internet connection, we have full control of everything that those tentacles have sort of got. So we've got our platform. There's the dashboard on the left, which is one of the cool oil and gas companies. We've got the 3D environment, which the robot can operate in. So we're basically stealing Spot's coordinate frame and saying, hey, Spot, do certain things in the environment. And then we've obviously got the DroneDeploy platform where we visualize a lot of the data in terms of imagery and 360 content. And the benefit of having this all cloud-based is that anyone can log in from anywhere in the world. So I can log in now if we want. We can go to a robot in Houston, get it around, do some industrial inspections, or we can jump into a robot that's in India building a hospital, which is actually quite cool. So anyone can log into anywhere, from anywhere, provided you have an internet connection. A lot of the time, all I'm doing is hotspotting off my phone. So that's a really cool function, which unlocks a lot of value in a robot being an autonomous solution wherever in the world. A little bit about our mission planning, workflows, and this is where things get complicated. You know, drones, you draw a map, basically a grid, the drone figures out where it needs to go, you deploy and off it goes. Our mission planning for ground robotics is a little bit different. And it's different because we've got all these sensors. We've integrated a bunch of sensors, and I'll show you a live demo, so I'll be real quick about this one. But basically, we've got a flow engine, which is a visual scripting environment, which means you don't have to be a programmer or you don't have to know any programming code. But if you do, you can do some really cool stuff. And basically what's happening there is we're starting a recording, we're telling the robot to go to a certain place. It then drops into a logical statement in the form of an if statement. And basically that if statement is looking for a condition. And that condition is saying, all right, get the gauge reading. So that gauge reading node is something that we've programmed that will send a image to a machine learning piece of kit, and it will return an answer and a confidence on that answer and all that type of stuff. And if we say, all right, the confidence is a certain level and the gauge reading is, above 25, then do something. And do something would be typically like send an emergency notification or take a photo, whatever it could be. If it's false, then it'll just carry on with the mission, stop whatever recording device is on it, load it to wherever it needs to go, and then basically they all end on the dock so that the battery can charge and get ready for the next one. Within this, you can see it can get like vastly complicated. We can just branch off and have all these different like thinking patterns that the robot can do. You can even call other actually, let's not get into that, it gets too complicated. But basically, you can see how advanced the mission planning can get for ground robotics because we have all these different softwares integrated, payloads, robot functions, all that type of stuff. All of that can be scheduled, obviously. We want to have these things happening. So that was, let's forget about that mission. I'll show you another mission in the live demo. But we would want that particular mission to happen at a certain time every day, and off it goes. But the reason we show this picture is that we can not only just start like basic missions to do something, We can also schedule in times when we want a specific action on the robot to happen or a specific action on a sensor to happen. So we've collected a bunch of data. We've got like 15 gigs worth of point cloud on there because the robot's done a whole cool thing. Problem is the corporate network's busy in the day, and if you start loading 15 gigs on the network, everyone starts complaining because bandwidth's gone. So we could potentially schedule in an upload function at midnight when everyone's at home, then it loads its data into the cloud, basically. So it's little things like that which are really powerful in this architecture breakdown that we've done. Remote teleoperation, I cannot show you this in real life, but I can show you a 6-minute video and get away with it. 6-second video, actually. Hopefully it works. So this is actually of a live site. It's basically using the thermal camera on the robot. The camera's on like a little mount, so the robot's not moving, but the mount's moving. It's got a 360 camera at the bottom, which gives us a full holistic view of where the robot is. Thermal imagery, we've flipped over to like this high quality gauge reading camera, which is really cool. And basically that's got like a 30 times zoom. And what it does now is it zooms up onto the circuit board and takes like a switchboard, takes a photo of that. And yeah, that's pretty cool. From our remote teleoperation, basically what I'm saying is that functionality is available to anyone, anywhere in the world with an internet connection, as long as they're invited to the project. They can get that robot up, operate it, plug an Xbox controller into the computer and operate it as if they're there. Sensor controls, take a photo, push it all up. So everything you see is available in a sort of autonomous way and also in a teleoperation way if you want to get manually involved. That customer in particular, typical energy workflow, they've got Spot on a dock. We've integrated their Spot payloads. They have got our agent online, our agents installed, which allows online offline connectivity. That's also something that is overlooked with robots and robot fleet management software. The robot always has to be online. With our agent installed, the jockey that's there, we deploy stuff onto that agent, and that agent keeps like a memory of it. So if we've got a schedule for a mission and it needs to run at this time, and suddenly the electricity goes out, I say electricity, the internet goes out, the robot needs power. The robot will still get up on that schedule, walk, and then keep that data with it. And when that internet connection is restored, we've obviously got a pipeline that goes and fetches it when it gets internet. Same thing if it walks into an offline environment. As long as the mission's deployed onto the robot, it can walk from an internet connection through your mine or wherever it needs to go, come out, and then upload the data onto the internet. So that's the offline capability. It's got predefined missions. It does 360 walkthroughs. It does these operator rounds, which is oil and gas specific. It's taking photos of gauges. It's taking photos of thermal imagery. Sometimes not this customer, but sometimes it's using sound, like I mentioned. And then this whole geospatial relationship, which I sort of briefed on, where we're starting to give coordinates. We're getting surveys in to give us coordinates of these. Either I do it or someone else, but we get coordinates of these. We load it to the robot. The robot operates in that coordinate frame, and then wherever that data is going, we transform it to have the right coordinates for whatever that use is. And that uploading is obviously autonomous. There's no sort of manual data transfer like the old days. This customer in particular is pushing all that data up into Amazon Web Service, where they've got this really cool machine learning team that goes and takes all these stuff, images and thermal stuff, and do some really cool things with the analytics on their plants. So a big use case for your repeat service inspection type companies. This customer is actually one of the biggest oil and gas service providers in the world, and yeah, they I guess the leaders at the moment. They get notifications, so every time the robot stands up, does a mission, every time it sits down, every time it gets lost, every time the battery goes up below a certain threshold, we're sending notifications and saying, you know, make attention to your robot, and you have an operator and a big screens, and he'll be able to log into that robot and move it back. And then obviously intervention, teleoperation. Basically, all those functions are available. Like I said, you can just jump onto that platform, get that robot up, get it back to the dock, or execute that mission again if you need to recapture that information in that same sort of order. So you can deploy these missions manually or autonomously. So a little bit of like a summary. It's got all the payloads integrated. It's got some third-party cool stuff. We've got its mission planning on schedules. They watch the missions, and we get these really cool reports, which is sort of the lower part of that darker image, where it reports everywhere it went, what photos it took, how long the mission was when it started. So obviously the statistics. They've got the teleoperation. And then the real cool thing is that Amazon Web Service integration, where it's doing all its analytics on that information that we've captured on those. That's actually yeah, that's what the gauge looks like. It's incredible camera, super high quality. It zooms right in on that gauge, and it's real smart because it's using machine learning. And this is remember when I spoke about like vendors creating integrations that don't do robot stuff really well. When you use Spot's native functionality to do that, Spot's actually using a lot of machine learning on its own to line up that gauge every time in the center. So you'll see if we watch the live mission, it will zoom up really close to a gauge and be off-centered. And then it like zooms out slightly and you'll see it slowly increments and basically figures out where, when it recorded it, what the area around it looked, lines it up and then zooms back in on that gauge. So if you put those in like a time lapse, you see this really solid center of the gauge in the time lapse fashion, dead in the middle every time, which helps obviously for machine learning because machine learning wants to see that gauge often. So that's what's happening on a big oil and gas site in the States. We'll be going there at July basically to go and deploy another one on another facility, which is very exciting. Typical construction, very, very similar to what I've said now already. Only difference is they are more survey focused and more sort of BIM workflow focused. So the idea of having a point cloud scanner on there all the time is obviously of value. This customer in particular is a very good example of a Leica workflow that's actually working really well in a construction sense. They've got RTC scanners that go out every single day, scan thousands of points, or I say millions of points. They've probably got like close to 60 to 100 stations a day that they scan. The entire site is like I can't say this out loud, but their control network's amazing. Every single column, almost every single column, 80% of their columns in one of the biggest data centers in the world, you can imagine how many columns there are, has a checkerboard target for scanning. So it doesn't matter where they set up their scanners, they always have control, and they'll always have like 15 control points wherever they scan. So really cool workflow from like survey to scanning. They chuck it through Register 360, which is awesome. And then they put it in a certain place depending on the purpose of the scan. And then they have this really cool downstream workflow that either does like hands-on, is there a problem here? Is things in the right place? Or it gets shipped off to another part of the world. And that does a whole, obviously, it implements the rest of their BIM workflow, which is like, obviously, record keeping for as-builds, updating models, and doing a whole bunch of cool other clash detection, which the first team might not have found. So a really cool way. Their only constraint is that they've got 2 guys doing scanning, and they can't actually get around site enough in a day. That thing solves its problem. It can get up, go to all these areas, scan, and have that information ready for them on their server in the B2G or E57 format so that they can just load that into register, or that off-site team in whatever country it is will go and pick it up and then carry on with that workflow without actually getting site guys involved. So real big efficiencies with laser scanning on the mobile sense. And they can do that because they've accepted that the quality of the scan is good enough for the efficiency benefits they get in terms of time of capture. So that's really cool. That's I'm actually off to go and see them on Sunday. I have to fly back to the States to go and implement the second stage of what we're doing there, which we can talk about in the future. Yeah, so construction summary, very much the same. Really cool dashboard that they've created. All that's customizable, by the way. We don't actually say that this is the teleoperation dashboard. You customize that however you want. You put whatever buttons you want, wherever you want. They've got the spot cameras plus a web camera. They've got a whole bunch of buttons that do cool things, and they've got other missions that are preloaded to do also fun things for construction site, really. But they've got this added function of LiDAR. And I guess a lot of what I've said might not make sense until I show you. So this is this hall, and we'll crack straight into it. So fairly easy. Old mate over here is called Frog. This time around, I don't know, someone in our office when we were all in San Francisco, and this robot arrived in Auckland, and we came back and it was called Frog. So we didn't have any say in that. But basically, this is what our robotics platform would look like. I'll jump to maybe a full screen. There's 2 robots. There's the Enterprise Auckland, Enterprise Auckland 2. So if we had a second robot online in the office, that one would be online. If our San Francisco robot's on, then normally that's online as well. And typically within our platform, we can jump into a robot in particular. It does look quite complicated at first, but this is a dashboard that's just diagnostics, and those tentacles I spoke about that are going into the robots, this is all our telemetry coming back from the robot in real time. So we can see how much of the CPU our agent is using, because obviously our agent's a piece of software that sits on that computer on the back. Obviously, we can make graphs out of it. There's a whole bunch of engineering, software engineering stuff that makes sense to very smart people. Kirsty said, I'm the expert. I'm not. I'm just a person who demos. The smart people understand all of this, which is pretty cool. Put it into context. This is what we call the live data viewer. Those tentacles that are in the robot with the backpack with all the different software looks like this, basically. And you can see here we've got a little part of our backpack called Leica. And within Leica, we can get a whole bunch of information through the API, which is all this like different language translation. We can say, all right, what is the capture status at the moment of the robot, and what is the capture state? And then we get information. So the minute I start scanning, basically it will give us a live feed of how many points the scanner's collected. So it just like obviously goes up in the hundreds of thousands, which is cool to watch. But we can see that it's finished. So it's in a finished state because I scanned before we started. And then, so that's the information I get from the robot. So the tentacles into the backpack of Leica tells me everything about that. And then I've got instructions where I can just say, hey, I want you to actually start that scan. So this is the very, very complicated way to look at how we sort of get into a robot or get into the sensors and coordinate them together. What the software does is basically takes all of these pieces of the puzzle and gives you the tools to link them together to do something efficient, right? And what that kind of looks like, if we jump into something like this, we obviously getting live telemetry from the robot. Like I said, we've got the information coming from the robot. We can send information to the robot. This yellow outline that you see is what I did when I created what we call an auto walk. We gave Spot an environment which it knows how to navigate. It did all these like little breadcrumbs basically, and if it had LiDAR, that would be super accurate, but it's using its vision cameras only plus the fiducials. So disclaimer, mate, we'll see what happens. As long as we don't stand in the way, I think we should be sweet. But basically anywhere on that yellow line, Spot knows how to navigate really well. And within its mission, if I had to block this, if it needed to go to B and A was here and I made a block here, it would give it a go maybe 3 or 4 times. And then once it can't get there, then it'll actually figure out another way, provided you've got a cool network of actually how to get there. So real cool dynamic stuff, which is a Spot specific thing. And go back to that thing. If other vendors out there who have created like points, laser scanning integrations, obviously not Leica, another one, you lose that functionality. Some of them, the Spot doesn't actually understand how to navigate smartly because they've lost the robot component, which we are trying our best to preserve. So we use the robot component to do robot things, like I mentioned. We get the sensor to do sensor things. What a mission looks like, and this is what I was saying with that workflow that gets very advanced. If you wanted to, let's say we've got this one called the BLK ARC. So basically, if we have a look at it, we do things like we acquire the lease. Acquire the lease is basically taking the reins of the robot and saying, we are in control now. And you can see if you look at a controller, that's typical Boston Dynamics controller, there's a button there that says hijack because we've stolen control from Boston Dynamics, basically. So I can't use that controller as it is. I have to hijack it from us, and then you'll see that we'll lose the lease, but that's not a problem. We acquire the lease. We tell Spot that we need it to localize in its environment so that it knows where it is. And basically, it needs to see the docking. It's always on the docking station. So it sees the docking station and it realizes that's where I am in my map. I'm all good to go. And then we run a bunch of things like undock. That's a robot command. Turn on the motors and stand up. Then we're using a navigation command to the robot that says, hey, go to that position, which is 73 at the top there. When you get to 73, what we want you to do is start the Leica scanner. And within that Leica scanner, it gives it enough time to initialize. Once that scanner is going, then we're basically going to do a Leica specific thing, which is like do a medium density scan. And that basically makes the robot stand real still for a while so that it can capture more points instead of just being sparse as it walks. And so we can basically send it around on missions to go to different places and do different things at different places. And once it's done, basically we can say, stop the scanner. Go back to a position that's very close to the dock, and then once you can see the dock, then basically dock. And the ID for the docking station in this case is 520. But there can be multiple docking stations on site. So if this was a massive site and you had a docking station on the other side that was port 521, you tell it to dock there, and then you would schedule in a mission that maybe does a bunch of rounds and gets it back to 520. And so your mission planning can become really advanced, which is really exciting for the robotics industry. So that's kind of how we plan missions. We can click along sort of that yellow area, and that's how the robot navigates around. So you can see it looks like it's taking a shortcut, but when I get the robot up and actually start moving it, you'll see that it creates like these breadcrumbs and follows them. We'll go back out of that. I guess you probably want to see a robot do something, which is why we're here. If I had an Xbox controller, I could use that. I can use these buttons, which do some cool things. Yeah, like I said, if I had an Xbox controller, there you guys all are, which is cool. You can take a photo of that if you want. Xbox controller, turn that on, navigate it as if I was using this Boston Dynamics controller. So the controls are the same, which is pretty cool. The other way of navigating, we might as well, let's give it a crack, is we use, like I said, we're doing robot things really well. So we're using the robot's navigation capabilities, and we're basically going to, like, let's say, hey, Spot, I want you to please go here. When you see the breadcrumbs, Spot's basically figure out where it is. It's going to end up going there. I've told it to walk downstairs backwards when I created this map. So you can see also my little man, Spot, seems to not be in the right place on this map. And we've probably got it's because of the light on it being on there at the moment. So there's a little bit of a weird thing happening with the way this map has been created. But that's a visual thing. It's not actually a positioning thing. So if I went to Spot now, I want you to go over there. Basically, it creates those breadcrumbs. Spot's using it. The robot knows how to navigate around. If you look closely at the robot, tabs again, there's Lennon. I can click the start scan button. So I've now clicked back on the dock. Basically, I want the robot to come back to the dock. It's chosen that going the way it came is probably the most efficient. If it wasn't, it would have come this way around, which would have been cool. But if it's going, it's still scanning, which is great. And then when it gets back here, I'll manually control it, and then we'll get an autonomous mission going if we want. But what I also would like to show in instructions to the ARC. So underneath those two buttons where my mouse is now, we're basically getting live feedback from the ARC saying what's happening, what are you doing? And we know that the ARC's running. When I go and stop that ARC scan, we're basically sending that instruction to the robot, to the backpack of the containers. It's obviously powering down. Once it's done, right, it just timed out, but it worked. So basically what's happened there is it stopped scanning, and we're getting live feedback from the scanner saying that it's finished. Easy. And then I can just click dock, and the robot hasn't seen the docking station. Let me just quickly move it forward because we don't want you to click the dock. Try again. There we go. So now that it can see the dock, I was standing too close to it, it couldn't see it. So now it can see the dock through its cameras, and we can dock it. So yeah, this is, again, like, how long does it take to walk around here? Maybe 30, 40 seconds worth of time to capture this whole thing. So far quicker than a normal scanner. And obviously there's a whole bunch of people here, which is not ideal in any scanning environment. But if you look at the walls and things like that, it's actually not that noisy. Like mobile map, that's obviously everyone's personal opinion on what they're using it for, but it's an incredibly impressive data set for only like 40 seconds worth of capture. So you can imagine if you slowed things down, you did it like really well, you added in some control, you did a bunch of other stuff, you could probably get something really usable in a very short amount of time. So there comes the value of actual mobile mapping in the long run, which is going to be exciting for, I guess, all industries, because oil and gas are a bit slow on actually adopting LiDAR, and they're actually driving it because they've also got some big cash where they're going to just, they want laser scanning. So get in there with lasers.
So first off, we have a question from Joshua Notman, who's asking about how you coordinate robot missions to horizontal coordinate systems and vertical datum. Is it just the standard as you would do with laser scanning targets? That's for you, Haydn.
Cool. Yeah, thanks everyone. Hopefully you can hear me. In terms of georeferencing your scans, it's probably going to be much the same, provided you've got good targets. But like I mentioned when we were talking, or during the live talk, we are trying to get the robot to operate within the coordinate frame. So applying control to the robot's control, or your survey control to the robot's control, and having the robot operate in that survey frame, obviously to the accuracies of what the robot can do, but typically you would still want your survey control to just tighten things up.
Just a follow-up question on that one. How does the stability of the robot affect the accuracy of that?
That's the beauty of mobile mapping. Stability of the robot is accounted for in the entire mobile mapping SLAM type process. So that's why mobile mapping on robots is probably more beneficial than terrestrial scanning. Terrestrial scanning on a robot, you've obviously stability of the robot. The robot's always compensating for how it's standing, weight shifting, so there is slight movements within the robot. So typically terrestrial scanning, unless there's a very good compensator within your scanning solution, you probably either want to have the robot lying down so that it is as stable as possible, or somehow lock out the motors in a mechanical way so it does stay fixed and level. But yeah, basically the mobile mapping takes care of any movements, hence the value of mobile mapping.
Awesome. We have another one here, which is about the other robotic carriers that you were showing in one of your slides. So obviously this presentation is all about the Boston Dynamics dog. How does that compare to the other devices that you've been looking at?
So I guess the answer to that is all about the robot's capability. So each robot manufacturer has their own secret sauce on how they get robots to do things like navigation and sort of waypoint mission type things. So when it comes to the other robot manufacturers, yeah, it purely depends on, we don't really focus on making the robot navigate better. It's all about the capabilities of those individual robot suppliers. And Boston Dynamics, I did mention it a few times, is very, very capable in terms of their user interface and the simplicity of just allowing the robot to navigate reliably and create an environment without much issue. So each robot has their own capability in navigation. Some robots, might get lost. Some robots might struggle to be repeatable in a sort of autonomous way, but Boston Dynamics in particular is very good at this stage. So as the robot industry develops, and so do SLAM navigation algorithms, so each robot's capabilities will improve.
Awesome, thank you. With the Boston Dynamics dog being a quadruped, how does that compare to some of the other devices? Is there limitations of it being a quadruped?
Yes, there are. Every robot's made for a specific purpose, every form factor, right? So tracked robots tend to be better in some environments than wheeled ones, because obviously a single slip, if there isn't a lock differential, you'll have some issues. Quadrupeds are great for stepping over obstacles, climbing steps, and also very uneven terrains where obviously rolling might be an issue for a robot that's sort of on wheels with a small wheelbase. Quadrupeds are able to sort of walk around, like you see in this picture, basically on steeper slopes, on more loose vegetation type stuff, as well as, yeah, like I mentioned, obstacles and stairs. So every robot has a purpose for a different place. And it's all up to, I guess, the decision of what robot you're going to choose is going to be relevant for your environment.
Awesome. And we have another question that's just come in from David Stewart. Can we expect that airborne robots with advanced crash avoidance functionality will eventually supersede the need for walking or rolling robots? Do you have any thoughts on that, Haydn?
there's some thoughts around that. It would be nice because that will, a few limitations on sort of ground obstacles will be avoided. But if you can imagine how the drone industry had to struggle to get compliance and acceptance that there would be something unmanned above their heads at lower altitudes, I think having things even lower, just above head height or within buildings, might also be a tough one to get over the line in future. But definitely, I mean, there's always that option. We'll see where the industry goes. I don't believe robots in the ground entirely will become unnecessary. I think there will always be a place for ground rover type applications.
Great. And at Global Survey, we've got one of the new Leica units coming, the VLK to fly. This will have obstacle avoidance so that you can fly through buildings, but that part isn't fully developed yet. Currently, we're focusing on the outside applications where it will be doing LiDAR mostly on like bridge applications. We should have that unit in the country in the next month. So if you're interested in finding out more about that one, we'd be happy to do a demo.
Yeah, just a follow up on that one as well, Kirsty. Robots indoors, like I mentioned in the sort of brief comparison between robots and drones, a lot of the navigation capabilities of drones at the moment rely on having GNSS reception and being able to have position information coming from your GNSS type sort of setup. Whereas anything indoors or on the ground has the limitation of how does it operate in its frame and how does it repeatedly operate in that frame and know where it is in its space so that it can obviously make it back to the dock or actually execute the mission successfully. So having a drone inside will then obviously require some very smart navigation capabilities like the robots have in order to position itself successfully and repeatedly in a sort of GNSS denied environment.
Sorry, you were cutting out a little bit there, but I think I got the gist of what you were saying. Can you still hear us?
Yep, I'm still here.
Yeah, definitely. Hopefully the future's going more in that direction though. Do we have any more questions from anyone? Okay, I think that is it. No more questions have come in. So thank you everyone for attending. Thank you so much, Haydn, for this amazing presentation. I've definitely learned a lot from you over the last few days with the integration between the ARC and the Boston Dynamics Spot. So thank you again to you and your team for making that possible. We also want to thank Becca, who hosted the in-person version of this event. And if you are interested in hosting a future Arch and Z event, please contact us at Global Survey and let us know. And as always, if you have any feedback, please get in touch. And if you would like to present, also email us at info@globalsurvey.co.nz. Next time, we have a presentation from Woods from their laser scanning and GIS team leads, talking about St. Stephen's School at Bombay, and they're all talking about geospatial data processing, management, and visualization. Thank you.